This video is going to be about Newton's third law of rotational motion. Newton's third law of rotational motion states that if body A applies a torque to body B, then body B applies an equal and opposite torque on body A. You might remember that Newton's third law applied to linear momentum. This form of Newton's third law we're going to apply to angular momentum, which we'll represent with the capital letter L. Just like it sounds, angular momentum is the rotational equivalent of linear momentum. It's the product of a body's moment of inertia and its angular velocity, which we would write as moment of inertia angular momentum L is equal to moment of inertia I times angular velocity omega. Just like linear momentum, it is a vector quantity, and the units of angular momentum we're going to use are kilogram meters squared per second. Angular momentum is related to torque, just like linear momentum was related to force by a similar equation. Net torque is equal to the change in linear momentum over the change in time. Just like change in momentum over change in time gave you net force, or average force, change in angular momentum over change in time gives you net torque. Now let's so just like linear momentum, angular momentum is also conserved. So when net torque on a system is 0, then the angular momentum of the system is conserved. So let's apply conservation of angular momentum to this ice skater here, and we'll see how changing her moment of inertia changes her angular velocity. So when she has arms out wide, her moment of inertia is very large, and she spins slowly, meaning she has a small omega, or a small angular velocity. So when her arms are wide, I is large, omega is small. When she brings her arms in, she'll spin faster because bringing her arms in reduces her moment of inertia. And in order to conserve angular momentum, her body must spin faster. So her angular velocity, omega, speeds up. It becomes faster. If we were to write this as an equation, because there's no external torque acting on the skater, we know that her initial angular momentum, when her arms are wide, has to equal her angular momentum when her arms are out, or arms are brought in. So the angular momentum is equal to the moment of inertia times the angular velocity. So the initial moment of inertia times the angular velocity, initial equals the final angular momentum, or final moment of inertia times the final angular velocity. And so when initial momentum, or the initial moment of inertia is large, that means you can have to have a small speed. And when your final moment of inertia is small, that means you can have to have a fast speed, so that both of these terms equal each other. So let's apply this to another example that has some numbers put to it. So in this example, a spherical star of mass m and radius r rotates about its axis with angular speed omega. The star explodes, ejecting mass into space. The star that is left behind has a mass of 1/10 the original mass and a radius 1/20th of the original radius. So we need to calculate the new angular speed. So we know the initial angular momentum has to equal the final angular momentum. And so the initial moment of inertia times the initial angular speed has to equal the final moment of inertia times the final angular speed. Okay? So if I look up the moment of inertia of a sphere, I see that it's 2/5 the mass times the radius squared. And the star's initial momentum was omega. Okay? And then its final moment of inertia, it's still a sphere, so it's still 2/5, but the mass is 1/10 of its original mass, and the radius is 1/20th of its original mass, radius. squared. I'm trying to find the new final omega. I solve for, so my 2/5 cancel out, my mass cancels out, my radius cancels out, and I end up with my initial omega is equal to my final omega divided by 4,000. So the final omega is 4,000 times the initial omega. Okay, that's it.